All right, so last topic to cover for this chapter is Lewis acids and bases. So let's go back through and look at some of our previous definitions of acids and bases. So we had the Arrhenius definition. And so this one was give H plus or OH minus in water. So that was specific to only water, right? And then Bronsted and Lowry came by and they said, wait a second, we don't just have to be talking about water. We can be talking about giving or taking H plus in any solvent. It doesn't have to be water to be an acid or a base, right? So our definition got more general. So let's take a look at an acid-base reaction. So we have AH, our acid, plus our B, our base. And so in this reaction, what occurs is that a lone pair from the base forms a bond with the hydrogen, and then the electrons in the AH bond go on to the A, the acid, right? And so you get an A minus plus a BH positive in this case, right? Not always plus or minus, depending on what the initial charge was, but we have a movement of electrons. And so that's where this guy Lewis came by and said, hey, wait a second, if we're talking about acids and bases, we don't even have to be talking about H pluses. Let's focus on these electron pairs instead. Right, so he said, let's call things acids or bases, whether they're donating or accepting H pluses. And so we can see here in this drawing right here, this is the acid, right? It donated the H plus, so that's an Arrhenius or Bronsted-Lowry acid, but it's also a Lewis acid. So a Lewis acid, he defined this as an electron pair acceptor. An electron pair acceptor, while he said that bases are electron pair donors. Right? So we're not even focused on the H plus anymore. We're just talking about whether it's accepting or donating a electron pair. And so just again, a Lewis acid is an electron pair acceptor. So you can remember kind of acid acceptor. Or you can draw an acid-base reaction yourself and then think about instead of focusing on the H plus, focus on the electron pair instead. And then, of course, a Lewis base is an electron pair donor, right? So again, we're just focused on the electron pairs now. Our definition is getting more and more general. So let's take a look at some common Lewis acids and some Lewis bases. So Lewis acids have to accept an electron pair, and so they're often hypovalent atoms. Because these hypovalent atoms have empty orbitals, right? These orbitals aren't filled, and so they could accept electrons into these orbitals. So for examples, BH3, aluminum H3, BCl3, and then aluminum chloride are probably your most common examples of Lewis acids, right? And these are all hypovalent, right? They only form 6 valence electrons as opposed to the normal 8. And then the other example is going to be transition metals. Transition metals will often act as Lewis acids because they have empty d orbitals that electrons can go into. So we'll focus on the transition metals a lot more in the following chapter, and then we've got a whole chapter on transition metals and coordination compounds. Lewis bases, on the other hand, are electron pair donors, and so if they're donating an electron pair, they have to have a lone pair to donate, right? How are you going to donate a lone pair if you don't have one in the first place? So the most common examples are ammonia, NH3, right? That's got a lone pair. And then water, that's also got a lone pair. So think previously we saw an aluminum coordinated to 6 waters. That's a Lewis acid base reaction. Probably the most common Lewis acid base reaction is between ammonia and BH3. So ammonia NH3 has this lone pair, and so it's going to donate them to this boron to form this Lewis base adduct. And so now this nitrogen has a positive charge and the boron has a negative charge. And so you see there's been no transfer of H's here. So we're not talking about a regular Bronsted-Lowry acid base. We're talking about a Lewis acid base. This nitrogen was the one that donated its lone pair, so it is the Lewis base. And then this BH3 is what accepted the lone pair, and so it was a Lewis acid. And then the product is called a Lewis acid base adduct, or otherwise known as a coordination compound. Sometimes you'll see an arrow instead of a bond, something like that. That's becoming less and less common, but that's just to indicate where the electron pair is coming from. It's coming from the nitrogen to the boron. You see, this bond formation is different than a lot of the other covalent bond formations. Usually in covalent bonds, you have a sharing of electrons, right? Each element gives up 1 or 2 of its electrons to share them, whereas in this Lewis acid base adduct, we have the donation of an electron pair. One element gives a pair of electrons, while the other one basically gives nothing. So if you go to organic chemistry, you'll learn a lot more about Lewis-based adducts and a lot more about these arrow pushing diagrams. I just want to show you one important example for us. So we have water and carbon dioxide. And so what will happen is that water and carbon dioxide will react with one another. So the lone pair on this oxygen will attack this carbon. And then one of these bonds is going to kick off the carbon, because carbon can't form more than 4 bonds, and go onto this oxygen. Now you have an extra lone pair on this oxygen and this negative charge. And then you have a positive charge on this oxygen. And then the next reaction is that this oxygen will attack this hydrogen, and then the lone pair from this bond will go back onto this oxygen to form your final product. And then if you think about what this is going to be H2CO3, or carbonic acid. So this example demonstrates how carbon dioxide can interact with water to form carbonic acid. So all the CO2 that we're pumping out from our cars and from our industry is interacting with the water either in the atmosphere or in the oceans to form carbonic acid, which is then helping to acidify the oceans and whatnot. And so you don't have to know how to draw this arrow pushing diagram. That's basically organic chemistry. So don't worry about the arrow pushing diagram. Just know that water and CO2 interact to form carbonic acid. And then you want to know which one's the Lewis acid and which one's the Lewis base. So in this case, the water was what donated the electron pair. And so this is the base. And then the CO2 accepted it. And this is the acid. One final thing to cover is that these definitions aren't separate from one another. They just get either more general or more specific. So every single Arrhenius acid is also a Bronsted-Lowry acid and is also a Lewis acid, just like every square is also a rectangle, right? However, every Lewis acid is not necessarily a Bronsted-Lowry acid, and a Bronsted-Lowry acid isn't necessarily an Arrhenius acid. Just like a rectangle isn't necessarily a square. So it's just all about how specific the definition is.